The buck converter, also referred to as a step-down converter, is a popular topology in power electronics that converts a higher input voltage to a lower output voltage. It is crucial in various applications, from portable devices to automotive systems, where specific components or subsystems require a lower voltage level to operate. The primary advantage of the buck converter is its simplicity, which enables efficient voltage conversion using a relatively small number of components. The operating principle of the buck converter involves controlled energy transfer from the input to the output through switches, an inductor, and a capacitor. A high-side switch, usually a MOSFET, and a low-side switch, typically a diode, are employed in the buck converter to control the current flow through the inductor. By adjusting the duty cycle of the high-side switch, the average output voltage can be regulated proportionally to the input voltage. When the high-side switch of a buck converter is switched on, it allows current to flow through the inductor, which stores energy in its magnetic field. This stored energy is then transferred to the output, charging the output capacitor and powering the load. When the high-side switch is turned off and the low-side switch is turned on, the inductor's magnetic field collapses, releasing the stored energy and maintaining the current flow to the load. The buck converter is designed to operate within a closed-loop control system, where a feedback mechanism continuously compares the output voltage to a reference voltage to ensure that the output voltage remains stable and regulated, regardless of changes in input voltage or load conditions. Circuit topology and key components. Figure 1 shows the circuit diagram of the buck converter, which consists of a source of DC power supply E, a switch S, typically a MOSFET or IGBT, a diode D, low-frequency bandpass LC filter and load R. The transistor is represented by a switch S with a small arrow, which marks the direction of the current that can be established through the switch. When the switch S is turned on, the diode D becomes inversely polarized by the supply voltage E, and the voltage across the inductor becomes equal to the difference between the supply voltage and the load voltage. See Figure 2. The current flowing through the inductor will increase linearly from the minimum to the maximum value. See Figure 3. If you want to watch Electrica Engineering video like this, click the subscribe button and press the bell icon. Thanks.